1901 Cass, West Virginia. The mountain air hung thick with coal smoke as a peculiar locomotive clattered into the logging camp, its vertical cylinders hissing steam in rhythmic bursts that sounded nothing like a proper railroad engine. 3-geared trucks rolled beneath a boiler mounted off-center, the entire contraption looking more like a factory machine mounted on rails than anything belonging to the world of railroading. No streamlined profile, no driving rods connecting massive wheels, no engineering elegance that made traditional steam locomotives the pride of railroad lines. Just exposed gearing, offset boiler, and a design that violated every principle railroad engineers had spent decades perfecting. Modern engineering wisdom said speed defined railroad success. Bigger driving wheels, longer boilers, higher steam pressure that pushed locomotives to 60 miles per hour across prairie main lines. The railroads promised rapid transit, where steel rails and powerful engines eliminated the barriers of distance and terrain. Yet in 2025, those same modern diesel-electric locomotives sit idle at the base of mountain grades, their computer-controlled traction systems defeated by inclines that would make highway engineers blanch. While a 120-year-old Shay locomotive still grinds up slopes approaching 12% grade with nothing more than exposed gears and relentless mechanical advantage, the most decisive engineering contradiction in railroad history wasn't written in horsepower ratings or programmed into electronic controls, but cast into geared trucks using principles that made torque more valuable than speed. Tom Bradford ran his hand along the Shay's gearbox housing, feeling the warmth of lubricant heated by constant friction. The 1913 Shay sat quiet in the roundhouse at Cass Scenic Railroad, its 70 tons of iron and steel smelling of hot oil and coal smoke even at rest. Steam wisped from relief valves as he checked pressure gauges mounted on the offset boiler. "Gearbox was rebuilt last season," Tom called to his fireman Jake, who was inspecting a modern diesel switcher near the turntable. "Still meshes smooth as butter." He listened to the idling engine, 3 vertical cylinders driving a line shaft that powered all 12 wheels through bevel gears. No slippage, no binding, just constant transfer of power from steam to steel. The Shay's frame carried the boiler mounted to the right of centerline, counterbalancing the weight of cylinders and line shaft on the left. Unconventional placement that horrified traditional locomotive designers, but necessary to accommodate the geared drive system that defined the machine's capability. Each truck could pivot independently, flexing with track irregularities that would derail rigid-frame locomotives. The gearing itself represented radical departure from standard practice. Rather than driving rods that connected to fixed wheels, the Shay used beveled gears at each truck, allowing constant power delivery. Regardless of wheel position, each 90-degree rotation of the cylinders translated to multiple wheel rotations through gear reduction, multiplying torque at the sacrifice of speed. "Tom, this diesel won't even attempt the upper grade, Bev," Jake said, consulting the operations manual for the modern locomotive. "The manual says the maximum sustained grade is 4%. The bald knob line hits 11% in places." Tom nodded, patting the Shay's weathered boiler jacket like an old friend. That's why Ephraim Shay built this girl the way he did. Ephraim Shay never intended to revolutionize mountain railroading when he started sketching designs in his Michigan lumber camp in 1877. The frustrated logger had watched conventional locomotives struggle and fail on the crude tracks that served his timber operations, their rigid frames derailing on rough roadbed, their direct drive system spinning wheels uselessly on steep grades. But he carried an idea that would outlast every high-speed locomotive design invented in the next century. Gearing first, then power. Build a machine flexible enough to follow tortured track alignments, then gear it low enough to convert modest steam pressure into irresistible pulling force. The physics hadn't changed since Shay's day, Tom knew, even as he explained the principle to Jake beside the idling locomotive. Torque equaled force multiplied by radius. A conventional locomotive with 60-inch driving wheels generated impressive speed but limited pulling power. The Shay's 36-inch wheels, driven through 3-to-1 gear reduction, sacrificed speed for torque that could move mountains. "Gearing is the secret sauce," Tom said, pointing to the exposed beveled gears that connected line shaft to truck. Every revolution of those vertical cylinders turns the line shaft once, but each truck wheel rotates 3 times. Triple the mechanical advantage, triple the pulling power. The mathematics of tractive effort followed principles that civil engineers understood instinctively. Conventional locomotives relied on weight on driving wheels and coefficient of friction between steel wheel and steel rail. On grades approaching 10%, gravity's pull exceeded friction's grip. Wheels spun, locomotives stalled, trains rolled backward despite engineers pouring sand on rails and opening throttles wide. Jake examined the Shay's truck assembly, noting how each axle connected to the central gearbox through universal joints that accommodated the truck's pivoting motion. But conventional locomotives have way more power, bigger boilers, higher pressure. How does this little geared engine outpull them? Tom smiled and pulled up performance specifications on his clipboard. A Baldwin Consolidation 280 generates maybe 40,000 pounds tractive effort with its 8 driving wheels. Impressive on flat ground, useless on mountain grades. This Shay generates 35,000 pounds, but delivers it through all 12 wheels with gearing that never loses traction. The Lima Locomotive Works, which purchased Shay's patents in 1881, built over 1,700 of these geared engines before production ended in 1940. Every single one documented with the same precision that characterized Bridgeport's machine tool manuals. Gear ratios, cylinder dimensions, boiler specifications, truck pivot angles, everything an engineer needed to maintain and rebuild the locomotive for decades of service. Modern diesel builders operated under different assumptions. Horsepower and speed defined success in an era when mainline railroads competed with highways and airlines. Better to design powerful road locomotives that could haul 100-car freights at 50 miles per hour than cater to specialized applications like mountain logging and mining. But the mountains didn't care about horsepower ratings or aerodynamic efficiency. Steep grades demanded torque, delivered through wheels that maintained constant contact with rails. The Shay's gearing provided exactly that, governed by mechanical principles unchanged since Archimedes invented the lever. The morning test run began with Jake building fire in the Shay's firebox, coal smoke rising black against the West Virginia dawn. Tom watched steam pressure climb on the gauge, noting how quickly the vertical fire tube boiler generated working steam. The offset design placed the firebox directly above the engineer's station, radiating heat that made summer operations brutal but provided instant thermal response. "Pressure's at 160, Jake called from the fireman's side. "Ready when you are?" Tom eased the throttle open, feeling the locomotive respond with immediate authority. No wheel slip, no hesitation, just smooth engagement as steam drove the vertical cylinders and gears transferred power to all 12 wheels simultaneously. The Shay rolled forward at walking pace, its distinctive exhaust beat sounding like a factory machine rather than a railroad engine. The track ahead climbed steadily, rising 300 feet in less than a mile. 11% sustained grade, the kind of incline that made highway trucks downshift into crawler gears and sent conventional locomotives searching for helpers or longer routes around the mountain. Jake monitored the water glass as the grade steepened, watching how the incline affected boiler water level. She's pulling steady, no signs of slipping. The secret lay in weight distribution that Shay had perfected through trial and error. Each truck carried equal load, approximately 12 tons per axle, creating consistent downforce that pressed wheels against rails. The flexible frame allowed trucks to conform to track irregularities, maintaining contact even on rough logging roads laid with minimal roadbed preparation. Tom had studied conventional locomotive failures on mountain grades, understanding why rigid-framed engines with fixed driving wheels performed poorly on steep inclines. As locomotives climbed, weight shifted rearward, reducing pressure on forward driving wheels. Those lightened wheels lost traction first, spinning uselessly while rear wheels still gripped. Engineers called it slipping the drivers, and it turned powerful locomotives into helpless machines that couldn't advance another foot. The Shay's articulated trucks eliminated this failure mode. Each truck pivoted independently, maintaining consistent weight distribution regardless of grade. When the locomotive climbed, all 12 wheels shared the load equally. When it descended, that same equal distribution provided braking force through all wheels simultaneously. "Grade's hitting 12% here," Tom announced, checking the clinometer mounted near his station. The Shay continued climbing without drama, its exhaust beat maintaining steady rhythm that indicated consistent power delivery. Modern diesel-electric locomotives generated far more horsepower than the Shay's modest steam plant. A contemporary EMD switcher produced 1,500 horsepower, dwarfing the Shay's estimated 300 horsepower output. But horsepower measured work over time, while torque measured rotational force. On steep grades, torque mattered more than horsepower. The gear reduction that defined the Shay's capability multiplied engine torque by 3, creating pulling force that conventional locomotives couldn't match without adding helper engines or doubling their weight. Lima's engineers had discovered what automotive designers would later prove with off-road vehicles. Low gearing and constant four-wheel drive conquered terrain that defeated more powerful machines. "Diesel's still sitting at the bottom," Jake observed, glancing back down the mountain. "We're halfway to Bald Knob and she hasn't moved." The Cass Scenic Railroad had operated as a logging line since 1901, when the West Virginia Pulp and Paper Company laid rails up Cheat Mountain to harvest virgin timber that conventional logging methods couldn't reach. The grades were brutal, the curves impossibly tight, the track alignment following terrain rather than engineering principles. Standard locomotives failed immediately. Baldwin consolidations, powerful engines that hauled heavy freights across prairie divisions, derailed on curves or stalled on grades. Shays succeeded where conventional power failed, their flexible frames negotiating 30-degree curves while maintaining full power to all wheels through gearing that never broke traction. Tom guided the locomotive through a horseshoe curve that wrapped around itself in less than 300 feet. The Shay's trucks pivoted smoothly, each following the rails without binding or scrubbing. A conventional locomotive with a rigid wheelbase would have lifted inside wheels off the rails or derailed completely. "This is what killed regular steam engines," Tom explained as they emerged from the curve onto another steep grade. "Rigid frame, long wheelbase, fixed driving rods. They needed a straight track and gentle curves. Shays were built for tracks that looked more like mountain goat paths." The logging railroads that employed Shays operated under constraints that mainline railroads never faced. Temporary tracks laid directly on forest floors, minimal grading, maximum grades approaching 14%, curves sharp enough to make the locomotive's front and rear trucks point in different directions. Track that cost $10,000 per mile instead of the $100,000 that proper railroad construction demanded. Jake consulted historical records that documented Shay performance across North American logging operations. Says here the Shays at Michigan California Lumber Company climbed grades to 13% while hauling 60-ton log loads. A standard geared locomotive couldn't pull 30 tons up the same grades. The comparison revealed Shay's fundamental advantage. A conventional consolidation might weigh 200,000 pounds, with 120,000 pounds on 8 driving wheels. Calculate tractive effort at 25% of weight on drivers, 30,000 pounds of pulling force. But on grades steep enough to reduce traction coefficient, that number dropped precipitously. The Shay distributed its 140,000 pounds across 12 driven wheels, generating theoretical tractive effort of 35,000 pounds. But the gearing and constant power delivery maintained that force even as grades steepened and traction decreased. Where conventional locomotives lost 30% of pulling power on steep grades, Shays maintained full power through mechanical advantage that couldn't slip. "The old logging bosses didn't care about speed," Tom continued as they crested the grade and emerged onto Bald Knob's summit. "They needed power that wouldn't quit. Shay gave them exactly that." The view from 4,800 feet revealed why conventional railroading avoided these mountains, grades too steep, curves too sharp, terrain too brutal for the efficient operation that mainline railroads demanded. But the timber was here. The coal was here. The resources that built industrial America waited in mountains that standard locomotives couldn't climb. Shays conquered this terrain not through brute force, but through mechanical cleverness that transformed modest power into irresistible pulling force. The maintenance manual for Lima Shay locomotives read like a machinist's encyclopedia, each component documented with the precision that characterized American industrial documentation from the era when manufacturers expected their products to be rebuilt rather than replaced. Page after page of exploded diagrams showed every bearing, every gear, every pipe fitting that comprised the locomotive's complex mechanism. Tom kept his manual in a fireproof cabinet at the roundhouse, its pages stained with oil and annotated with decades of maintenance notes from previous engineers. The book fell open to a cutaway drawing of the gearbox assembly, each component labeled with part numbers that Lima had honored for 40 years of production. "Everything's rebuildable," Tom explained to Jake, pointing to the gear train that transferred power from line shaft to truck. "These beveled gears wear out eventually, but you can cut new ones from bar stock if you've got a competent machinist. Bearings are standard sizes, seals are basic packing, nothing proprietary, nothing obsolete." The philosophy extended beyond simple component replacement to complete locomotive restoration. Shays that had worked 30 years in brutal logging service could be torn down, inspected, and rebuilt to better than new condition. Boilers were retubed, frames were straightened and remachined, gearboxes were disassembled and refitted with new gears and bearings. Modern diesel locomotives operated under different maintenance assumptions: electronic fuel injection systems, computerized engine management, emissions control systems that required specialized diagnostic equipment and proprietary software. A diesel engine might run 1,000,000 miles between overhauls, but when major components failed, replacement often proved more economical than repair. Jake examined the Shay's exposed gearing, noting how easy access made inspection and lubrication straightforward. "Diesel manuals barely mention internal repairs. Everything's sealed, everything's a complete assembly replacement." Tom nodded, pulling up cost comparisons he had compiled over years of maintaining both steam and diesel power. "Complete overhaul on this Shay. New tubes, rebush all bearings, repack glands, rebuild gearboxes runs maybe $80,000. Returns a locomotive that'll work another 30 years. The same money might get you a used diesel that'll need major engine work in 5 years. The economic logic was inescapable for operations willing to invest in restoration rather than replacement. The Cass Scenic Railroad maintained 3 operational Shays, each rebuilt multiple times over their century-plus service lives. The mechanical simplicity that railroad engineers had once criticized as primitive now proved to be Shay's greatest advantage. "The Lima engineers designed for disassembly," Tom continued, showing Jake how major components could be removed without specialized tooling. "Gearbox comes out as a complete unit. Cylinders unbolt for valve work. Even the boiler can be lifted off the frame for major repairs." They expected these locomotives to be maintained in small backwoods shops with basic equipment. Modern preservation operations proved the wisdom of this approach. Museums and tourist railroads across North America operated Shays that had been out of service for decades, restored to operation by volunteers using the detailed documentation Lima had provided. No proprietary parts, no obsolete electronics, no vendor lock-in that prevented independent repairs, just iron, steel, and bronze components that followed maintenance principles unchanged since the Industrial Revolution. The demonstration run began with both locomotives positioned at the base of the test grade, a mile-long climb that averaged 9% and peaked at 11%. The modern diesel-electric switcher represented contemporary motive power, 1,500 horsepower, microprocessor-controlled traction management, and dynamic braking systems that could stop a runaway train through electrical resistance alone. Tom watched from the Shay's cab as the diesel engineer opened his throttle, computer systems calculating optimal power delivery to maintain traction without wheel slip. The diesel accelerated smoothly, pulling 10 loaded log cars that represented typical Cass operations. 200 yards into the grade, the diesel's wheels began hunting for grip. Traction control systems modulated power to each axle, trying to maintain forward progress as the grade steepened beyond the locomotive's capability. Sand sprayed onto rails from automated dispensers, providing temporary friction that bought another 100 feet of progress. Then the diesel stopped, its wheels spinning uselessly despite computers' best efforts to manage power delivery. The engineer backed down carefully, dynamic brakes controlling descent as the heavy train rolled backward to the grade's base. "Physics doesn't care about horsepower ratings," Tom said to Jake as he opened the Shay's throttle. The geared locomotive engaged with authority, pulling the same 10 cars the diesel had failed to move. The exhaust beat settled into a steady rhythm that indicated consistent power delivery. The Shay climbed without drama, its gears transferring steam power to all 12 wheels through mechanical connections that couldn't slip. No electronic traction control, no computerized wheel slip detection, just constant torque that pushed the train upward through pure mechanical advantage. Jake monitored the water glass and firebox, maintaining steam pressure as the locomotive worked against gravity. "We're pulling steady at 6 miles per hour. Diesel was doing 12 before it stalled." The speed difference illustrated the fundamental trade-off that defined the Shay's capability. Conventional locomotives optimized for speed, their large driving wheels and direct drive systems designed to convert steam pressure into rapid rotation. The Shay optimized for torque, its gearing sacrificing speed for pulling force that could move loads up grades where faster locomotives failed. Modern railroad economics favored speed over power. A diesel that could haul a 100-car freight at 50 miles per hour generated more revenue than a slower locomotive with superior pulling force. But specialized applications still demanded Shay's unique capabilities. Logging railroads didn't have schedules to meet, Tom explained as they crested the grade and paused at the summit. They needed to move timber from forest to mill, regardless of how long it took. 6 miles per hour that actually moved loads beat 12 miles per hour that stalled halfway up. The principle extended beyond logging to mining operations, industrial switching, and any application where terrain defeated conventional motive power. Shays worked copper mines in Arizona, coal operations in West Virginia, sugar plantations in Hawaii, anywhere steep grades and tight curves required locomotives that could deliver power in conditions where standard designs failed. The diesel sat silent at the base. Defeated by grades, the century-old Shay climbed effortlessly. The afternoon sun cast long shadows across the cast roundhouse as Tom wiped lubricating oil from the Shay's gearbox inspection ports. The locomotive had completed another flawless run-up, bald knob, its century-old mechanism performing exactly as Lima's engineers had designed in 1913. Jake documented the day's performance in the maintenance log, noting steam pressure, water consumption, and the diesel's failure on grades the Shay conquered without difficulty. "I still can't believe a 100-year-old locomotive outpulled modern power." Tom closed the inspection covers and checked oil levels in the gearbox reservoir. "That's because you're thinking about it wrong. The Shay didn't outpull anything. It was designed for completely different operating conditions than mainline locomotives. Comparing them is like comparing a mountain goat to a racehorse." The distinction mattered more than mechanical specification. Ephraim Shay had recognized that logging and mining operations required capabilities that conventional railroading couldn't provide. Rather than trying to adapt standard designs to specialized applications, he created an entirely new locomotive type that abandoned speed for power, rigid frames for flexibility, elegance for utility. Lima Locomotive Works built 20,700 Shays between 1880 and 1945, each one serving operators who needed power in places where conventional locomotives couldn't function. When logging moved to accessible terrain and highways carried freight that railroads once dominated, the Shays found new work in industrial switching, mine operations, and eventually preservation of railroads that valued their unique capabilities. "Over 70 Shays still exist," Tom said, pulling up preservation statistics on his tablet. "Maybe a dozen operational, another 20 under restoration. Compare that to conventional locomotives from the same era where 99% went to scrap." The survival rate revealed something fundamental about the Shay's design philosophy. Locomotives built for easy maintenance, documented for independent repair, and optimized for specialized work, rather than general service, proved more valuable than more sophisticated designs that couldn't be maintained once manufacturer support ended. Modern railroad engineering had rediscovered some principles the Shay embodied. Contemporary mountain railroads in Switzerland and Austria employed rack and pinion systems that used gearing to climb grades approaching 25%. Electric locomotives in mining operations used multiple motors for constant power delivery. Even modern diesel hydraulic locomotives borrowed the Shay's principle of using fluid couplings to multiply torque at low speeds. If we paired those old Lima engineering principles with modern materials and manufacturing, Jake suggested, could you build a better mountain locomotive? Tom considered the question while securing the Shay for the night, draining water from cylinders and setting brake shoes against wheels. Maybe. Lighter alloys, better bearings, more efficient steam generation. But the fundamental concept doesn't need improving. Ephraim Shay figured out that some jobs need power more than speed, flexibility more than rigid efficiency. The locomotive stood silent in gathering darkness, its weathered boiler jacket bearing scars from decades of brutal mountain service. Built to climb where conventional power failed, designed to be maintained by operators who understood mechanical principles rather than computer diagnostics. Engineered to last generations rather than planned obsolescence cycles. A forgotten steam engine that conquered terrain modern locomotives still can't climb.